Hello, everybody. So I was getting kind of tired and sick of doing the voiceovers, so I wanted to do something different for the notes today. So that's why it's in this format. So this is our introduction into rocks and minerals, and unfortunately, I can't have all of you here to intro you into it. So I feel like this is the next best option. And of course, as you're listening, if you have questions, just pause the video and shoot me an email and I'll try to get back to you as soon as I can. So first of all, you rock. What is a rock? So a lot of times when we're talking about rocks, people are just like, oh yeah, this is a rock, but they don't actually know what it is. So the official definition of a rock is a solid mixture of one or more minerals. And we've heard of rocks before and we've seen rocks. So if you were here in the classroom, I would ask you to throw out some ideas of rocks that we've heard of before. A lot of times people, well, I don't need to write them down, but people have heard of granite. A lot of people have granite countertops. Slate is a pretty commonly known one. Marble. Maybe you've heard of sandstone or limestone. These are all different types of rocks, and they're just made of different minerals. So if you're critically thinking, you should have another question right now. What's a mineral? Oh, here are some examples of rocks. And know that there are lots and lots and lots of types of rocks. Okay, so what is a mineral? So similar to being a planet, a mineral also has to check all the boxes off. And if it doesn't check off one of the boxes, then it doesn't get to be called a mineral. So a mineral has to be solid. It has to be naturally formed, which means we can't be making it in a lab or something like this. It has to be non-living and have come from something that was non-living. So if you've seen Jurassic Park and you've seen the part where they have the mosquito in the amber, a lot of people think, oh, that amber, it must be a rock or it must be a mineral. But the amber actually came from tree sap. So that came from a living thing. So amber is not considered a mineral. It also has to have a crystalline structure, which means that the atoms are organized in a way that gives it some sort of structure rather than something like glass. In glass, there is no structure to it. It's all kind of just melty. So glass is not considered a mineral. So examples of some things you may have heard of before are things like aluminum and copper and quartz and salt and ice. Ice is actually a mineral. Water is not, because it is not solid, but ice is a solid and it has that crystalline structure. All right, so we've got minerals, and if you take a bunch of minerals and put them together, that's when you get a rock. Okay. A lot of people also ask me at this point in class, so what's a gem? So just for your own knowledge, very quickly, a gem is basically just a fancy polished off mineral. So the picture on the left here is a picture of a diamond, but it's the mineral form. So we would take that diamond right out of the earth. And it's obviously been cleaned off a lot more than if we just pulled it out of the ground. But once you polish it off and cut it nicely and make it really pretty, that's when it's considered a gem. So a gem is basically just a human construct. It's just a pretty thing that we like to have. This is another example of the ruby mineral is actually called corundum. And it might look something like this. And then once you polish it off and make it look pretty, it looks like that nice ruby on the side there. So the next challenge that I would give you if you were in class was to try to find a way to arrange these words into some sort of diagram. So you have rock, atom, element, mineral, and gem. So we just talked about rocks, minerals, and gems, and atoms and elements are a little bit of review about the periodic table. So we know that atoms are the smallest thing, and when you have a bunch of atoms together, that's going to create an element. So try to, like, if you're taking notes, which I would suggest you're doing, try to make a picture that organizes these words visually. A lot of times people will draw something like this where they have, oh, and I'm sorry, I don't have atoms on here. So it would be atoms are the smallest and they make elements. If you have a bunch of elements together, you make a mineral, which could also be called a gem if you shine it up. And then a bunch of minerals together make a rock. So a lot of times people will make some sort of image like this, but I've seen a lot of really creative ways to organize these couple words. This is one of my favorite pictures. It shows the world's largest mineral, which is in Mexico. It's called the Cave of Crystals. And if minerals have space and time to grow, they will actually grow much, much bigger. So I don't know if you've ever had like a geode before, which looks gross on the outside, but if you smash it, it has like all those purpley crystals on the inside. So those crystals have been given time to grow and space, and they're able to grow kind of into that opening. So that's why if you break it open, sometimes you get that really pretty crystals on the inside. This is the same thing. It's kind of like a gigantic geode. And if you've been noticing the white pictures, I have them there because this is a mineral called gypsum. It's 36 feet long, and those are the people to scale. So these crystals are absolutely huge. So the longer you give time for a crystal to grow and the more space you give it, it can grow into something absolutely gigantic. And I just think it's really cool. So how do rocks form? This is kind of all of this has been leading up to how do rocks form. And hopefully, I'm really hoping that this is some review for you. So there are 3 different ways that rocks can form. You can either melt a rock and then harden it. That would be like that first picture there, like lava. You can take a rock and you can add heat and pressure to it, and you can actually form it into a different rock. Or you can take an existing rock, you can weather it, erode it, move it somewhere else, deposit it, and then basically glue it back together, and that creates a rock as well. So these are the 3 different rock types, which I'm hoping that you have a little bit of background in. So depending on how the rocks form, whether they melt and solidify, have heat and pressure added to them, or they go through the breaking up, moving, and then turning into a new rock phase, you get a different type of rock. So we have igneous rocks, sedimentary rocks, and metamorphic rocks. All right, so we're going to start with igneous, which is everyone's usual favorite because it's so fun and explosive. There is a nice link here to a video that helps describe it if you want to kind of watch a video on it. So igneous rocks, you want to think of melted rocks. You want to think liquid rock that at one point is actual liquid. Normally we think of volcanoes. Now you know we can think of divergent boundaries as well, where the magma is coming up. All of that is creating an igneous rock. And igneous rocks can cool in different ways. So if the magma comes shooting out of a volcano, it's going to cool really quickly because relative to the middle of the earth and around all the other magma, the air is much, much colder. So it cools really fast. And if you remember back to the minerals picture that I showed you a few minutes ago, I said that minerals, if they have time and if they have space, they can grow really large. But this thing is coming rocketing out of a volcano. It's hitting the air. It's cooling extremely fast. And so it doesn't have any time to make those crystals. So the minerals are still in there. They're just much smaller. They don't have time to grow into something really pretty. So when we get igneous rocks that are coming out of a volcano, there are such small grains that you really can't see them at all. Those are called extrusive rocks. And I remember that like extrusive is like exit. So these things are exiting the volcano and they're cooling really quickly and we don't get any crystals that you can see with your naked eye. However, not all volcanoes explode. So if you look at the picture that I have here, you can see that there's like this magma chamber, and the magma chamber goes in a couple different directions. So one of those that's going off to the left, that is actually never going to explode out of a volcano. It's still liquid down there, but it doesn't come out of the volcano. And that allows that rock to actually cool very, very slowly. So here it does have time to grow the crystals. And because it has time to grow those crystals, the minerals appear much larger and you can actually see individual crystals in the rock. So if you've ever seen granite, like a granite countertop, or some buildings have granite in them, when you look at a piece of granite, you can see there's black chunks and there's white chunks and there's some pinkish chunks. Those are the actual minerals and crystals that had time to grow. So if it was liquid at one point, but it doesn't explode and it actually cools inside the earth, it's going to cool really slowly because the whole earth is insulating it, and we call it an intrusive rock. And intrusive because it's in the earth. Okay, so that is igneous rock. All right, moving on to metamorphic. So while igneous is a lot of people's favorite rock because it's very explosive and exciting and it's really easy to picture melted rocks, metamorphic might be some of people's least favorite rocks. But metamorphic rocks have really, really interesting histories. Again, there's a video link here if you want to go watch that. So a metamorphic rock, you take a rock that already exists. And what you do is you add heat and you add pressure to that rock. And basically by squeezing it or by heating it up, you're actually cooking that rock into something else. The major difference is that it doesn't melt. You don't cook it so much that it melts into a liquid, because as soon as it melts into a liquid, it's an igneous rock. So you're going to take your metamorphic rock, you're going to heat it up there's different amounts that you can heat it up. You could heat it up a little bit and it would become one type of metamorphic rock, or you could heat it all the way up right to before it melts and you'd get a different type of metamorphic rock. So the amount of heat and pressure that you add to it can also change the rock. So really important to remember igneous versus metamorphic. This one is cooked. And I put cooked because we're not obviously like putting it in the oven. You could not get the oven that hot. These igneous rocks are melted. Cooked, but no melting. That's the major difference that people have a lot of hard time wrapping their heads around. So if you're thinking critically and you're thinking about cooking rocks and adding heat and pressure, your next question should be, how? How can you add heat and pressure to a rock? Because like I just said, you're obviously not like putting it in the oven. You're not going out there and squeezing the rock yourself, and that wouldn't add enough pressure anyways. So how is it possible to add heat and pressure to rocks? So there's two examples that I have here. The first one in the like upper right hand corner is called contact metamorphism. Basically what happens is a rock gets cooked by some magma that's nearby. So if I had a rock that was already existing in an area, let's say we're under the ocean or something, my green ocean, and maybe I have some layers of rocks underneath the ocean. And for some reason, maybe some magma comes up through here and melts these rocks. So if it melts these are going to turn into igneous rocks. but it's only going to touch. It might melt like along the edge here, making this edge igneous. But right here, it's not touching the magma, but it's really close, and this magma is really hot. So sometimes this area can actually get cooked by this magma coming up. It's not melting, it's just getting hot enough that it can change it into a metamorphic rock. Okay. So that's the first way, contact metamorphism. And you can just think of it as like contacting. There's magma that's contacting the rock and heating it up. So that would be contact metamorphism. Oh, I messed up my word. Okay, the second one is called regional metamorphism. And regional metamorphism is happening over a really large region. Contact metamorphism is happening in much smaller areas where the magma is, but regional metamorphism happens in large areas. So the first one that's easy to kind of wrap our heads around is at convergent plate boundaries. So remember, at a convergent boundary, the plates are coming towards each other. And especially if you're at a continental boundary where they have the same density, neither one wants to go down. So what happens is they start pressing against each other. And if you do this with your fingers, you can see that it's creating a lot of pressure, and it hurts my fingers. And then eventually they're going to go up. But that creates lots and lots of pressure and also heat. So you're building a whole region, like a whole mountain range, like the Himalayas, are metamorphic rocks because they are slamming into each other and adding all this pressure as they build. Another way that you can have regional metamorphism over a big span is in this picture here. They have some layers of rock. Okay, and they have this, and they also have water. And what happens is over time, and we'll get to this one in a second, sediments that are in this ocean are going to be falling on top. And they come off the land and they settle on the ocean floor. Eventually, this will become a sedimentary rock, which we'll talk about in a second. And then more will land on it. And we get another layer of sedimentary rocks. As we stack more and more and more and more up on top, the bottom part starts to get a lot of pressure on it. It'd be like if you built, you started with like a 5-person pyramid, but then you started adding more and more and more people on top. The people on the bottom would start to get squished. So that's kind of like what's happening with that metamorphic rock. The weight of all these sediments can push this, and eventually high pressure will change this into a a metamorphic rock. Okay. So metamorphic rocks are different from igneous rocks because they're cooked but not melted. And ways that we can get to add that heat and pressure is either through contact metamorphism or through regional metamorphism over large areas. All right, the last rock type, sedimentary rocks. I've already alluded to this a little bit, but a sedimentary rock is basically just pieces of old rocks or dead creatures or some chemicals sometimes, but basically it's pieces of other things that get glued together. And the way that they get glued together is by different minerals and chemicals that are in the water, which we'll get to in a second. So the first thing for a sedimentary rock is that you have to weather an existing rock. So if you hopefully have learned the word weathering before, but let's say that I have like a nice mountain here, okay? And over time, we know that the mountain is going to get rained on, it's going to get snowed on, and pieces of this mountain, especially like this pointy tip, this little piece of rock eventually is going to break off. Maybe a person kicks it or something, and breaks that chunk of rock off. So that would be weathering. Weathering is breaking the rocks. One way I remember it is like if this was a rock, if you break the rock, that's weathering. See the lovely W? So weathering is breaking a rock. So the first stage, the first thing you have to do in order to make a sedimentary rock is break an existing rock. Then that piece of rock needs to go through erosion. So erosion is the movement of the rock. So it's going to head on down our mountain here. And if we take that W for weathering and we tip it over and we do this, woo, it's like erosion. So weathering is breaking, erosion is moving. So now I need to take my rock and move it down slope. Okay, the next thing I need to do is deposition. So I'm going to do a different scale here. So if my mountain is here, here's my piece that's eroding down the mountain. Eventually it's going to get to the base of the mountain, and rocks really don't like being above sea level. Their main goal in life is trying to get back to the ocean. So it's going to head down, it's going to find its way into a nice river, and eventually it will find its way out into the ocean. Here's let's see, can I draw a shark? And shark. Beautiful. Yes, you all love my drawings. So not to scale, but so first we're going to weather the rock, then we're going to erode it, then we're going to move it, and eventually my rock is going to erode, it's going to move down the river, and when it gets to the big ocean, the ocean is going so much slower than the river is. Like the river is kind of rushing towards the ocean. And then when it gets there, it's just like, you're free, and lets go of it, and it lets the particle that came from the top of maybe Camel's Hump out, and it drops in the ocean. That's called deposition. So if you look at that top picture that probably my picture is covering a little bit, you can see all those little pieces that are coming off, and they are falling on the bottom of the ocean. So it's starting to make these layers. So weathering, erosion, deposition, then we have to take those layers and compact them. So we have to add more and more and more on top of them. So I have, all right, we're going to a profile view now, kind of what they have drawn there. So my rocks are eroding, they're depositing on the bottom here. Actually, I'm going to draw them bigger. Not to scale. So they're all falling here on the bottom, and they're going to get compacted, and they're going to get squished, and as more falls on top of it, it's going to look something like this. Okay, but now all that we have is sand that came from the top of Camel's Hump, and it got down, and it landed at the ocean, and now we just have a layer of sand. So if I want to turn it into something like sandstone, which is just sand that's been cemented together, I need a way to glue all of these pieces of sand together. Because right now it's just sand. So what happens is in the water, there are little chemicals. And those little chemicals and minerals, they work their way through all these little cracks and crevices, and they deposit some of the minerals that are in them inside the cracks. And over a long time, we can fill all of the cracks with this mineral water. And now this has become a sandstone or any type of sedimentary rock. So a sedimentary rock is just, you take an old rock, you crush it up, you move it somewhere else, you usually drop it in the ocean or a lake or something like that, and then over time, all those little pieces get glued together. There are different ways that you can weather rocks and break them up. So water can break them, wind can break rocks. A common one in Vermont is glaciers. As glaciers run over rocks, they chew them all up. Tree roots, if you've ever gone hiking in Vermont, you've probably seen tree roots wedging themselves in between rocks. That can break rocks. And then my favorite is ice wedging, which, well, not my favorite, but that's where water is able to sneak itself into a crack. And then at nighttime, it freezes. And when it does that, it expands. And then the next night, 2 little water droplets can get in. And then they freeze and expand it. So if you've ever been driving on the roads before and you see those huge cracks in the road, that's from ice wedging, because it's really wet in Vermont and it's also cold. And so water droplets get in there, and as they freeze, they bust the road open. Same thing happens to rocks. So these are all ways that we can break rocks down. You can also change rocks by chemically weathering them. So things like rusting can change, acid rain can break down rocks, and then fire and combustion can also chemically change stuff. So these are just some different ways that you can do this first step of breaking that rock down from like the top of Camel's Hump. At the top of Camel's Hump, you're usually dealing with physical weathering, water, wind, tree roots, and things like that. So here are just a couple pictures. The top left is pebbles. So you can see that all those pebbles, they didn't start out like that. They probably started out on top of a pointy mountain, but because they've been in a stream for so long, they've gotten nice and rounded. The second one is of wind. So wind has like eaten the bottom of that rock out. There's a biological one, the ice wedging one, and then the other picture is the glacial picture. And this is one of my favorites because this is something that we see in Vermont all the time. So as glaciers moved over mountains, and let me remind you, the glaciers in Vermont were like 2 miles high. So they totally, completely covered Camel's Hump, Mount Mansfield, all the mountains here were covered in glaciers. And as the glaciers came down from the north, they were churning up as much as they could of the rocks beneath them. They're basically like scraping the ground. And when you have a glacier and it goes over a mountain, it creates this shape in this picture right here. So it creates like this kind of a low angle side. And then on the back side of it, it plucks off pieces and makes a much steeper slope. So we get something that's like, and then steep, if the glacier is moving this way. Just try to think if you've ever seen something like that in Vermont before. Camel's Hump. So Camel's Hump is a perfect example of this feature created by glaciers, where it's coming up from one side, and then it would be coming in this picture, it'd be coming from the right side. The glacier is moving to the left side of the picture, and as it comes over the left side, it like pulls the side off of Camel's Hump, so we get a low angle slope, and then a much higher angle slope on the backside. Those are some of the physical weathering. And then here's just an example of chemical weathering. Rusting is an example, and caves is a really cool example, all the stalactites and stalagmites. So after we go through weathering, erosion, deposition, compaction, we get to cementation. So that's the gluing. And that's where I was saying that you have all these minerals that are in the water, and they come out of the water and they glue these pieces together. And you've seen this before. So if you've ever seen a shower head that looks like this in the locker room, or at your house, if you have hard water, this happens at people's houses all the time, especially on older, what are they called? Fixtures that have been there for a while. That is showing you minerals that are in the water, and they're coming out of the shower head, and over time they can build up and you can see them. Same with the toilet. I know it's not the best picture, but if you have rust in your water, or iron in your water, I should say, it creates like a reddish color, and that might create a ring on your toilet bowl right where the water sits, because over time it's depositing that iron onto the toilet. So that's exactly what I'm talking about when it glues these sand grains together. It's just these minerals that you have seen on shower heads and in toilets that are actually gluing all this stuff together to make rocks. So, kind of cool. So then it brings us all the way back to the rock cycle. So we have the 3 types of rocks. We have the igneous rocks. We know they're melted. We have the metamorphic, which are the cooked rocks, and the sedimentary rocks, which are the pieces of broken rocks. And the cool thing is that any rock can become any other type of rock or itself. So if you take a sedimentary rock and you melt it, it's going to become igneous. And then if you take the igneous rock and you add heat and pressure to it, it's going to become metamorphic. And then if you take that metamorphic rock, break it up, move it, deposit it, glue it back together, sedimentary rock. But the sedimentary rock could also weather, erode, and get glued together into a different type of rock and become a different type of sedimentary rock. You could have a metamorphic rock that you add heat and pressure to, and it becomes a different type of metamorphic rock. Or you could add so much heat and pressure that it melts, and then you've turned it into an igneous rock. So the rock cycle is pretty self-explanatory in that it's a cycle, and it can become anything that it wants to be. Let the rocks do what they want to do. So this is just an activity that if you were in class, I'd have you do. I'm not going to make you do it at home, but try to figure out like what pieces are missing without going back and looking at the answers. So there is a short assignment. I have linked it here, but you also probably want to access it through Google Classroom just so that the links work out. You're going to just do a quick rock cycle assignment where you're going to drag and drop some words, just to make sure that you're kind of following along with rock cycle and rock types. Of course, if you ever have any questions, make sure to email me. I would also love feedback on if you like this style of notes better, or if you like just a click on the audio on each slide. So feedback like that is helpful. All right, have a great rest of your day, and I will see you later.